Okay, so you guys, for example, really quickly, I'm going to write down a couple complex numbers like 2 plus 4i would be an example of a complex number. But you can also use irrational numbers. Like I could do like the square root of 3 minus 4i, something like that. Okay, you can have those. Now we say every number is a complex number. So like a real number is a complex number. It just wouldn't have the imaginary part. The imaginary part would be 0. So like 5 plus 0i. But do we write plus 0i when we have 5? No, we just usually write it as 5. Okay, so you can make any real number. Like an imaginary number, the real part is 0. Like 0 plus 8i. But we would just write that as 8i. Now, for your assignment today, whenever you have a pure imaginary number, you're just going to write it as a complex number. You're just going to put C for complex. That's why I didn't put an abbreviation for imaginary, because that's how the way the people that are developed these lessons wrote it, and so we're just going to say consistent with that. Okay, so real numbers are any number you can put on a number line. I would write that down. Real number is any number you can put on a number line. We wrote that down last time, didn't we? Okay, so don't worry about it. Okay, and then rational numbers. Rational numbers are numbers that can be written as an integer divided by an integer. Like 6 is a rational number, but it can be written as 6 over 1. Okay, and any terminating decimal, 0.25. 0.25 is a rational number. It can be written as an integer over an integer, like 1 over 4 is 0.25. Irrational numbers are those numbers we talked about that if you, like square roots of non-perfect squares, if you take the square root of that, it has a decimal that goes on forever and does not repeat a pattern. Or pi. No, because they go on forever. Okay? How do you know there's trees in the forest if you've never been there? How do you know the moon exists if you never touched it? Okay. Because someone's done this before. They couldn't find the end. Okay. Integers. Integers are these numbers right here. How many of you guys know what that means when I put that notation like that? Well, this means that, yeah, but what does the ... mean at the end? It repeats that pattern forever. So, guys, an integer is a whole number. It goes on a whole number or its opposite. Okay? Do you guys know what the difference is between whole numbers and integers? Say that again. Whole numbers don't have negatives. So whole numbers start at 0, and they go this way forever. Okay, and by the way, the book doesn't have, or this lesson doesn't have natural numbers in it, but natural numbers are sometimes called the counting numbers. And guess what the only difference between the whole numbers and natural numbers are? No 0. That's it. I don't know. Well, when you start counting something, do you start at 0? And that's probably why, I'm guessing. Okay? So, anyway, those are the numbers. Now, you guys, I hope you wrote these letters down, because on the assignment, we're going to do it right now, you have got to write down, like I'm going to give you a number. It's going to be, let's say I give you the number 7.35. Let's say this is the number I give you on your assignment. And I say, and the instructions are going to be list, this number goes under what category? And you're going to list them all. Well, first of all, you're going to determine, is this a real number or imaginary number? A real number. So you're going to start at real number right over here, and you're going to go down. Okay, it's a real number. Now, so you're going to put an R by that. And then, is it rational or irrational? Rational. It's rational, right? It's got to be one or the other. And then you're going to say, is it an integer? It is not. So you stop right there. So you're just going to have an R and a Q by 7.35. Okay? Yeah. And then what if I gave you the square root of 7? Okay? Oh, by the way, you should also put C. It's complex, it's real, and it's rational. For 7.35. For 7.35, you should put C, R, and Q. Okay, for square root of 7, what should you put? For square root of 7, what should you put? C, R, and Q with the line over the top, right? Irrational. Okay? Irrational numbers are still real numbers. Okay? What if I gave you I square root of 2? It's an imaginary number, so you're just going to put C. If I just put C without an R on it, I know that that C is an imaginary number. That's why you don't. So just put C. You don't have to put imaginary number. You don't have to put anything for imaginary. Do you understand what we're doing? Natural number, don't worry about either because it's not part of the list on the assignment. So just go on. Okay, you guys, I'm going to hand this out to you. I'm going to give you 2 minutes to do problems 1 through 9. Yes. Okay, you guys got 2 minutes. Go. Yeah. Okay, you guys got 2 minutes, starting right now. Go. Anything you don't get done is homework. Okay, all eyes right here. Okay, the next thing we're going to be doing is we're going to simplify radical expressions. Okay, now, if you look at this, the thing you need to know about radical expressions, all eyes right here, you guys. The thing about radical expressions is you can only, they're like terms. You can only add them together if the radical is the same radical. In other words, the number inside is the same, the radicand. So, like, I have the square root of 2 here. The radicand is 2. And the index is also 2, even though we don't write it in. If all of these are the same, if any two radicals are the same, you can add them together. They're like terms. Okay, so you just add the numbers in front of them. Like, if you have 5 square root of 2's plus 8 square root of 2's, that makes how many square root of 2's? 13. 5 plus 8 is 13, right? Minus 2 square root of 2's is 11. So your answer is going to be 11 square root of 2. Now, since the 7 doesn't have a square root of 2 in it, it's not a like term. Order of operation doesn't allow us to add them together, and you would leave the expression like that, okay? Now, what I want you to do right now, I want you guys to do 11, 13, and 15. Circle those problems, 11, 13, and 15 with your shoulder partner, okay? Or if you got a group of 3, just do it in a circle, okay? And I'm going to give you a few minutes to do those, and then we're going to move on. 11, 13, and 15, okay? Go. Okay, you guys, on number 13, really quickly. You guys, 8 breaks down into 2 times 4, and 4 breaks down to 2 times 2. So you have a pair of 2's and a loner 2, right? One of the pairs, put it on the outside, the loner back inside. So 2 root 2. Loner goes inside. One of the pairs goes outside. 18 breaks down to 9 times 2. 9 breaks down to 3 times 3. You have a pair of 3's, a loner 2. So this breaks down into 3 root 2. Okay, you take one of the pairs, put it on the outside. 32. 4 times 8 is 32. 2 times 2 is 4. 2 times 4. 2 times 2. So I have a pair of 2's there, pair of 2's there, loner 2 there. Take one of those pairs and one of those pairs, times them together. 2 times 2 is 4. And the loner back inside. root 2. 2 minus 3 is a negative 1. Negative 1 plus 4 is 3. So your answer is 3 root 2. I saw several of you guys had that. Good job. Some of you guys didn't. Okay. Do we get it? Last time we were in class, we learned about I. We learned that I equals the square root of negative 1. What did we learn I squared was equal to? Negative 1. Remember that? Okay. And because think about it, it would be the square root of negative 1 squared. Because if you look at it this way, the square root of negative 1 and you square it, because that's I is the square root of negative 1, the square root and the square undo each other and you get negative 1. That's why I squared equals negative 1. Now, you also need to know what I cubed is and I to the 4th is. Well, if we already know that I squared is negative 1, we can rewrite I cubed as I squared times I, right? And what is I squared equal to? Negative 1. Okay? And I never rewrite it as the square root of negative 1. I just write it as I. So negative 1 times I. What's the most simple way to write negative 1 times I? Negative I. So you need to know that I cubed is a negative I. And then I to the 4th. What is I to the 4th? I squared times I squared, which is negative 1 times negative 1, which is positive 1. So I to the 4th is a positive 1. Now, you know what the cool thing after this is? It repeats pattern. You did this already, huh? Okay, so it just repeats the pattern. Like if I gave you guys I to the 53rd power, that would be a lot of i's to write out, I squareds to write out, right? To figure out what it is. But what we do, I show students in a couple different ways. I have I, and then I have, I'm going to go around this way, negative 1, negative I, and positive 1. Okay? So that's I squared, I cubed, and I to the 4th. But what happens is this keeps repeating the pattern. Because if I had I to the 5th, let me just show you really quickly. I to the 5th can be I to the 4th times I, right? And I to the 4th is what? 1. And 1 times I is I. So I to the 5th is the same thing as I. I to the 6th would be the same thing as I squared. I to the 7th, same thing as I cubed. I to the 8th, the same thing as I to the 4th. And we'd continue that. I to the 9th, I to the 10th, I to the 11th, I to the 12th. 13th, 14th, 15th, 16th. So all multiples of 4, every time you land on 4, 8, 12, 16, 20, 24, and so forth, you're going to get 1, right? So I to the 53rd, you can just check this by saying, finding what the remainder is when you divide 4 into 53. What's the remainder when you divide 4 into 53? Okay, because it will go into 52 is what you're saying, right? Okay, because we know that 4 will go into 48 12 times. So it'll go into 52 13 times with 1 left over. So I to the 53 is the same thing as I to the 1st power, right? Okay, and you get I. Another way you could do it, I wrote this thing right here, I, negative 1, negative I, and 1. I've had students do this. They count like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52. Did I miss one? Oh, 52, 53. I'm sorry. 53. I, right there. I like the first method I showed you better, where you divide 4 into it, and whatever the remainder is, That's what it is. But, huh? Does it have to be 4? No. Okay, so, yeah, it has to be 4 because I to the 4th is 1. Okay, got it? All right, so what I want to do is show you guys, I want to talk about simplifying expressions that are going to have imaginary numbers. Now, there's 2 ways you could do this, but there's only one correct way that's correct according to the order of operation. So you got to look very carefully. Everybody stop whatever you're doing. Watch this, okay? If I was to go -3 times -3, what would I get? -3 times -3 is what? +9, right? +9. And what's the square root of +9? 3. However, this is incorrect. That's the incorrect way. That's not order of operation. Okay? Order of operation says that we got to do exponents first. And in this case right here, and this actually we've got to do the imaginary numbers first. This really should be written as I root 3 times I root 3, right? Because you have the square root of a negative number. Every time you have the square root of a negative number, you're going to have an I. And then I times I is I squared, and square root of 3 times square root of 3 is square root of 9, right? And what's I squared, everybody? -1. And what's the square root of 3? 3. And what's -1 times 3? -3. The correct answer to this is -3, not +3. Yeah, you can. This is here. Look at this. Think of it this way: square root of -3 times the square root of -3. Square root of -3 times the square root of -3 is the same thing as square root of -3 squared, right? And the square and the square root undo each other, and so you get -3. I have to show you the order of operation. So,
but if you do it the top way,
if you do it the top way, you'll get it wrong. So you can't. This is the rule. You can't ever, when they're both negative like this, or if there's a negative inside there, you can't multiply them until you've taken care of the I. Yes. Yeah. Yeah, but you still have a negative that you got to account for, the square root of a negative number. Yeah, well, it doesn't have to be the same number. Look at this. What if I have the square root of -5 times the square root of -3? Okay? Well, I know that 3 times 5 is 15, right? But technically, I should have I squared of 5 times I squared of 3. And that's going to make I squared times the square root of 15, right? And what is I squared? So it's negative square root of 15 is the correct answer. Okay? Square root of -15. Okay, what I would like you to do right now is okay, just know this, you guys, if you don't have this written down. Don't worry about that right now. I'll go over that later on. You guys, hey, look, here's the answers you're going to use. Whenever you have I's, whenever you have a square root of a negative number, your answer should either be I, -1, -I, or 1 times whatever else there is, okay? So you know, that's how you express the answers if you're given any of those. An I squared would be a -1, an I cubed a -I, and an I fourth a 1, and a square root of -1 an I, okay? All right. Circle the following 3 problems. You're going to do those next. 16, 19, and 21. 16, 19, and 21. I'm going to give you 1 minute to do those. 16, 19, and 21. Go. Hey guys, the question is, someone asked, can I write -50i as -50 times the square root of -1? The answer is yes, it's an equivalent expression, but is not the simplest form. The simplest form would be write square root of negative 1 as I. Okay? Are there any questions on that one? How did you do it? Well, you had 2i times 5i squared, right? Now, the 2i is not being squared, just the 5i. So I have 2i times 5i times 5i, right? Because 5i squared means 5i times 5i. And then, so it doesn't matter which order you multiply these in. I times I times I, that's I cubed. What do we know I cubed is?
Negative I.
It's a negative I, right? So I know I'm going to have a negative I. And what's 2 times 5 times 5? 50. So negative I times 50 is negative 50i. Do you understand that, Christian? I times I times I.
On that step, could you change this by negative 1 and then make it 12 for negative 1? Where do you get 12?
You could change it in a lot of different forms, but that wouldn't be the easiest way to do it. I mean, you could go like this. I mean, I'm not sure what you're talking about. Change all the i's to square root of negative 1? Yeah, you could go 2 root negative 1 times 5 root negative 1 times 5 root negative 1.
And then add 5.
Not add. 2 times 5 times 5 is 50. 50, right? You're timesing. The square root of negative 1 times the square root of negative 1 times the square root of negative 1. Well, we know the square root of negative 1 times the square root of negative 1 is negative 1 times the square root of negative 1, right? And negative 1, square root of negative 1 is I, so it's 50 times the negative 1 times I. And 50 times negative 1 is negative 50 times the I, right? No matter which way you do it, you're going to get it, but that's by far the harder way to do it. If you know that you have I times I times I, that's the same thing as I cubed, and you already know that's equal to negative I. And then you go 2 times 5 times 5 is 50, so times that by 50, and you get negative 50I. Got it? Okay. Okay, now, you guys, let me explain something here. So far, when we've solved quadratic equations, we have always gotten rational numbers inside our square roots. So we've had problems like we're inside the square root. We have like 36 minus 2 times, I got to think of a good one here. Let me give you x squared plus 10x plus 24 equals 0. Let's say I have this problem right here. I have A, B, and C are 1, 10, and 24. Any questions on that? Okay, I need you guys, first a quarter, and I know some of you guys aren't concerned about your grades yet. You got to listen now. I'm not going to be so nice at the end of this quarter. I was way too nice at the end of the last quarter. Okay. I was way too nice. Okay. Okay. Well, we didn't test on the part we weren't done with.
Well, we're going to have to test on it now anyway.
No, we're going to just have the test on the part we haven't tested on. It's going to be a short test. Okay. So listen now, so you never get behind. Okay. You'll ace the first test. Hey, you guys, honestly, it's going to be a short test. You should ace the first test if you pay attention here. Okay. Now, so far, when we've done these problems, when we use the Pythagorean, or not the Pythagorean, the quadratic formula, we get a nice number inside of here. B squared would be 100 minus 4 times 1 times 24 is 96. And 2 times 1 is 2. What's 100 minus 96? And we all know what the square root of 4 is, right? What is the square root of 4? The square root of 4 is 2. Okay? Now, negative 10 plus 2 is negative 8 divided by 2, which is negative 4. There's one of my solutions. Negative 10 minus 2 is negative 12. Divided by 2 is negative 6. There's my other solutions. My solutions would be negative 4, negative 2. So everything we've done so far, don't write this down, guys. Everything we've done so far has a perfect square in there, right? I'm going to about make the most critical point of the year, of the new year so far. Are you guys ready? Okay. Kurt, is everybody as excited as Kurt is?
No.
I think he was fanning himself like this for a second. So, all right. So square root of 4 is a perfect square, and it's easy to do that one. What happens when we get a number that's not a perfect square in there? What if I end up with 5? What kind of number do I get? What kind of solution do I get? Irrational, right? I get an irrational. What happens if I end up with a negative number inside? Then I get an imaginary solution, right? So we haven't had any where we've gotten irrational or imaginary solutions so far. And so we're going to do that right now. So, I want you to do this one right here. We are going to want to solve this equation right here. Now, notice in this quadratic equation there's no b term. B is 0, right? Do I need to use the quadratic formula to solve this one? What can I do? Minus 18. I don't have to use the quadratic formula because the b term is missing. I can just minus 18 from both sides. Yeah. Now, what can I do to get x by itself? Look what happens here. What do I get? I get plus or minus the square root of a negative 18. All right? Okay? Now, so how am I going to write that solution? Okay? Well, I could write it as I squared of 18, but what about 18? Does it simplify? Yeah, because we know that 9 breaks down to 3 times 3 is 2, right? So 18 breaks down to 3 root 2. So it's going to be 3i root 2, plus or minus. Well, when I have the square root of negative 18, anytime you take the square root of a negative number, you're going to have an I, right? Let me rewrite it up here. Square root of 18 can be rewritten as the square root of negative 1 times the square root of 18, which is I root 18, right? And then 18 can be rewritten as 3 root 2. So I have 3i root 2. Now, why do I have a plus and a minus? Yeah, I have two solutions. Whenever you take the square root of both sides of an equation like this, you're going to get a plus or minus. That's why the quadratic formula has a plus or minus in it. Okay? That's because quadratic equations cross the x-axis twice. But if they don't cross it twice, like this, you're going to get two imaginary solutions. But remember last time I taught you that all quadratic equations are going to have two answers every time? Do you remember that?
Why would you want imaginary solutions?
Well, okay. Well, listen, you guys. Some mathematician a long time ago. Listen. Some mathematician gave it a bad name a long time ago. Because they use the word imaginary, probably because you can't see it on a graph physically, but this number still exists. Okay? The numbers exist, you just can't physically see it on the graph. That's why they came up with the number system. You can't physically see it on the graph. No. Because when a parabola can cross the x-axis twice, a solution to a quadratic equation is where it crosses the x-axis. And so you can see it, if your answer is rational or irrational, you can see it crossing the x-axis twice. Okay, but if it's imaginary, the parabola never crosses the x-axis. So physically, you can't see it on the graph. You can't see the solution on the graph. You can see the graph, But you can't, I'm saying there's still a solution. So there is a solution. You just can't see them. They're no longer x-intercepts. They're called roots. They're called roots. But you don't. You can't graph them on the graph. They don't exist on a graph. Okay. Hey, you guys. Why is everybody talking right now? Shh. Listen, please. Okay. I'm trying to answer your question. Listen. Okay. You know what? Every year I teach this. It's so funny. Everybody gets all mad because why do we have to learn this if they don't really exist? The thing is, they do exist. Okay? But I didn't say that. I says you can't see them on the graph. It doesn't mean they don't exist. Okay? Let me tell you this. When they first, guys, listen. When they first came up with the idea of imaginary numbers, there was no practical application for them. There is. In the world of electronics, they exist. Okay? And in order to solve them, David, stop talking. Thank you. Okay, in the world of electronics, they exist. Okay? If it wasn't for imaginary numbers, you guys wouldn't have iPhones or iPods or Androids today. Huh? Because there's a lot of problems that can't be solved because in the solution to the problem, you have a quadratic equation that has imaginary solutions. And usually what happens is it takes you into the imaginary numbers and then takes it back out to the real numbers. But in order to go through the whole process of solving them, you get imaginary numbers, but then it brings them back out into the real numbers. And so they can come up with solutions. I don't know all of it behind it because I don't work in the world of electronics. Okay? But I know that they exist there. I've read about them before. It's been a while since I've read about them, but I've seen problems where they've used them to solve problems in electronics. And that's why we have them. But you guys need to understand that they are there. They're actual numbers. You just can't physically see them on a graph, but they still exist.
Are we ever going to use this later in life?
It's kind of think of it as a bridge gapping you over to the other side. Okay? All right, we're going to move on. Okay, so let's do this one right here. Okay, I want you guys all in your groups with your shoulder partner. I want you to solve this problem right here. Go. There's the X right there. Sorry, you guys. Okay, all eyes right here. Some of you guys got this far right here and asked me if it was right. You were almost there, okay? The square root of negative 23 can be written as the square root of negative 1 times the square root of 23, right? And what is the square root of negative 1? I, so it's I root 23. Okay, so 3 plus or minus I root 23 all over 2. What, did someone else have a problem with some other part of it? I saw this a couple of times. I saw some of you guys had this. 3 plus or minus the square root of negative 41 over 2. If you did that, you know why you did that? Because when you had the... You get this inside. When you went b squared minus 4ac, you went negative squared and you got negative 9. Don't forget, negative 3 squared requires parentheses. You're going to always get a positive number there. And then when you minus the 32, you get a negative 23, not a negative 41. Okay? So that one's wrong. Okay? Any questions there? If you get a negative inside of there, you know you have imaginary solution. You know you're going to have an I. Do you understand that? Okay. All right. Everybody, do 23 and 25 in your groups. Go. 23 and 25. I'm just going to give you about 2 minutes. 1 minute on each one. Go. So I'm going to put this at the end of the recording. Okay? A negative number, you get 2 imaginary. Okay? A positive number, you get 2 real. And 0, you get 1 real. Now, yeah. Any problem on here that we didn't finish is homework. Get it done, okay? All right. See you guys.